Okay, hello and welcome to session Language Acquisition 3. We're going to have 5 talks, of which are 3 in person. And the first one is going to be virtual by Hao Zhu. I hope they are already there. All right, for now we can't hear you.
Can you hear me
it's
now?
good. It's good. Yeah, we can hear you.
Cool.
All right.
Hi everyone. Today I will present our recent work on building a computational framework to simulate children language acquisition for investigating the influence of cognitive goals and language input. This is a joint work with my advisors done at the Carnegie Mellon University. There are various theories proposed for the stimuli that are responsible for the first language acquisition. In this work, we mainly examine 2 hypotheses. In the first case, the children has the intention to get the teddy bear in the playground. If they use the word for rattle instead, the parent will give the rattle, which doesn't match the intention to the children. If they use a bear, the parent would understand the intention and give the teddy bear to them. In these 2 examples, rattle might lead to a negative reward, and the bear might lead to a positive reward. Through this kind of trial and error learning, a reinforcement learning machine learns to use the alternatives which match their intentions to maximize the expected utility. This kind of learning is often called reinforcement learning, or learning from communicative goals. The second case, they use a black teddy bear instead of brown bear to refer to the toy. In this specific situation, the parent guesses the baby uses the wrong adjective. So they give the baby a corrective feedback, which is also called expansion in previous literature. The baby tends to mimic the parent's speech due to their imitation desire. So this kind of noisy supervised learning, the child could also learn to use the correct language associated with their desire. The learning signal of this case is called the language input in this work. So to study the interplay between the 2 signals and their roles in language learning, we build a new referential game paradigm where the speaker, which models the baby, could generate utterances conditioned on its hidden intention, while the listener, which models the parent, could choose to make a choice and/or give feedback. Note that giving feedback is not always helpful since the listener may make a wrong guess. So within the framework, we study 2 research questions. The first research question is it possible to learn a speaker model, which models the baby, through playing with a skilled listener model, a grown-up? This is our hypothesis. The answer is yes, and it may not learn the exact language of the listener model. And the second research question is what are the roles of a communicative goals and the language input? Our hypothesis is that communicative goals should help with learning grounded expressions, while language input should mainly help syntax learning. So in our experiment, we study 2 different sets of referential games. Image referential games, where the goal is to refer to an image among different images, and object referential game that is referring to an object in an image. Here we use the latter one as an example. The speaker, which is a randomly initialized neural network, which encodes the object features and it generates sentences, sample and utterance based on the target object, which is the man sitting at the far end of the table. And the listener, which is a pre-trained object detector, makes its choice through generating a bounding box or not generate anything if it is not confident. That is called no op or no action. no opt will incur a small penalty, while wrong choices lead to larger penalties, and the correct ones lead to positive rewards. The reward is the communication goal signal, which is used for the reinforcement training of the speaker. The listener also has the chance to give a corrective input, which is sampled from the ground truth object descriptions for the object the listener guesses to be the target the speaker wants to describe. To simplify the listener policy, we use a confidence-based listener, which makes the decisions conditioned on the maximum probability of the target. The measure for confidence has its limit, but it is shown to be useful in many machine learning applications. We set two thresholds as a hyperparameter, C0 and C1. C0, sorry, C1 and C2. C1 is the threshold for not choosing any subject, not choosing any objects, and C2 is the threshold for giving feedback. The intuition behind the C2 is that the listener should only give feedback when it has the confidence on the guess and the utterance is not specified. It's not specified enough. We will study the individual effects of the two hyperparameters in this work. So here we show the performance of the model trained with the either signal or both of them. And we can show that the accuracy of the language input only model tops at 60% in both image referential game setting and object referential game setting. In the image referential game setting, models with a communication goal objective have significantly higher accuracy. However, the communication goal only model needs about 400K steps to warm up before dramatically improving on the similar performance of the combined model. With the help of language input, the model with both communication goal and language input not only has a faster improvement at the start of the training, but also achieve higher accuracy than the communication goal only model. In the object referential game setting, the communication goal only model can only reach as a high accuracy as the language input model. But the model with both signals can achieve significantly high accuracy. And the possible reason for the different results between the two settings is that the object referential games are more difficult because it also requires understanding the scene and adapting to a listener that has been trained on out of domain data. In this case, language input in language learning are more important than image referential games. In the second part of the experiment, we studied the factor that help fluency learning. In the first set of the experiment, in the image referential game, we found that the language input is in both of the settings, we found that the language input is the main driver for learning to speak more fluently. The improvement brought by language input may be the reason why the model trained with both signals doesn't need a warm-up as we shown before. So what about the listener strategy? So we have introduced how we build the listener based on its confidence and the definition of theta 1 and theta 2. Here we show the influence of theta 1 and theta 2 on the final game accuracy. And then we can find that both of the theta values make a huge difference on the final game accuracy And if it's not set well, the game accuracy will be just random accuracy. So we found that these two theta values are very important for building the confidence-based listening model. And here is an interesting phenomenon that we found brought by our model, the resulting model. Here are six pairs of images. In each pair, the image on the left corresponds to the concept, while the image on the right are also described with the same word in the referential frame by the best model we have trained, and found that the model learned to overextend the concept to other concepts belong to a higher category. So this is always called overextension in language acquisition literature. And it is interesting that we found that our model also have the same phenomenon. And here are the implications of this work on different communities. For the AI communities, the training the models to converse and learn language from human is an interesting topic. And the previous work has really explored incorporating the feedback from human, which, as shown in this work, accelerates the learning process and help learning to speak more fluently. And for cognitive science community, this is a computational framework to examine which hypotheses are computationally feasible. Researchers could compare the learning curve and the language skills learned by the models with humans. Here are a few take-home messages. Both communicative, in our work, we found that both communicative goals and the language input are useful for language learning in the referential game. The communicative goals appears to be the main driver, but the language input also accelerates language learning, especially fluency learning. And choosing when to give feedback is an important pedagogical strategy. And finally, similar to humans, model trained in this game also have interesting overextension behavior. So this concludes my presentation. I want to take the question now. Thank you.
Is there any questions from the audience? Or any questions online already, maybe? If not, I can start. I've in fact actually worked on a very similar model before, also learning grounded language from language input and feedback. And I was interested in the choice that you made regarding how you model the language input, because you also sometimes refer to it as feedback to the learner. So you have the reinforcement learning, but then this language input, which is at the same time also a feedback signal. So I was wondering whether why there was no input signal that was like independent of the behavior of the learner, if that makes sense. Like for me at the moment, it seems like all the input that the learner gets is always just in response to the learner's behavior. So it's always a feedback signal. But I feel like in the real world, children are also just exposed to language input without doing anything, like just if they are told something or if they overhear a conversation from some other people.
Yeah, this is an interesting question. This is I think this is the limitation of my work. This is obviously not the most realistic framework. It is not obviously not a direct replica of the real language learning scenario in human language acquisition. So in this work, we just study these two kinds of learning signals, and we for language input part, we only study the practice input based on the utterances generated by children. And this actually, in previous work, has shown to be take a large proportion of the language input of the children. It may take like as much as like 30% of all of the language input. Although the larger portion of that language input is still not not the corrective feedback, but maybe the conversation between parents or instructions parents give to the children. So this actually also play a huge role in language learning, for sure.
Okay. Yeah, I think it's something we always making progress on this modeling, but there's still many gaps to fill. Definitely. Yeah. Has there been any questions online in the meantime? If not, I have another question actually. So regarding the feedback, I was actually for my work wondering a lot how realistic it is, because you were framing, I think in one of the previous slides, that it is useful to learn these models using human feedback. Yeah, I think in the one of the last slides on the conclusion or something, that yeah, it's useful to improve these models using human feedback. But in this work, if I understand correctly, there's not actual human feedback, right? It's just a model that has been pre-trained on some data. And I was wondering if you have any ideas to extend this to actual human feedback, to put this model in the loop in conversation with actual human partners.
Yeah. Definitely. So that is definitely the work that we are currently working on and planning to do. The major problem with training with humans that the human won't wait for like the millions of steps to train the model, while the reinforcement learning model from scratch will take like a million of steps. So this is not feasible to directly use a human, at least at the first stage. So so our like current research setup is to like a pre-trained model with like not a perfect human data. For example, using the model I presented here, and the use model and incorporate human feedback after we have successfully trained this model, and hopefully that we can improve the model with just like a few thousand steps or a few hundred steps that a normal human partner could tolerate.
Cool. Yeah, very exciting. I'm looking forward to see this. Okay, I think then we can move on to the second talk. Thanks to the speaker again.
Okay.
And the next speaker is Chen Yu.